So alcohols are kind of like halogens in that they are substituted hydrocarbons, except instead of being substituted with a halogen, they're substituted with a hydroxyl group. And a hydroxyl group is a group that contains an oxygen and a hydrogen. It's a very polar group. You'll recognize this from water or from ethanol or from methanol. They're very polar molecules because they're able to hydrogen bond with their partners. And just like with halogen then, if we want to make an alcohol, we have to take off a hydrogen to make some room. And we have to add the hydroxyl group on like this. Now the naming is going to work a little bit differently. I'll show you how that works, but we will need a locant as well to tell us where the hydroxyl group is. So this guy, instead of being propane, it's going to be propanol. And it's going to be propan-1-ol because the hydroxyl is at the first carbon. Let's look at how we do some of these on the workbook. So like we said, alcohols are molecules which contain the hydroxyl functional group. And you have to be careful about those two words, right? Because we will sometimes call it an alcohol group, but really it's a hydroxyl group. So a hydroxyl group is an O bonded to an H bonded to some rest of the molecule. And we can use R to represent the rest of the molecule. Like we said, the hydroxyl has the ability to form hydrogen bonds with other hydroxyls. And that allows for hydrogen bonding between one alcohol and another alcohol. And remember from chemistry 20 that hydrogen bonding can happen when a hydrogen atom is bonded to a very, very electronegative atom like oxygen or nitrogen or fluorine, which strips away the electrons from the hydrogen, right? The hydrogen only has one electron hanging out over here, and oxygen is so electronegative that it pulls that electron density this way, which exposes hydrogen's positive nucleus, which makes this side of the bond quite strongly partially positive, and this side of the bond quite strongly partially negative. So it's a very polar bond and can interact very strongly with a hydroxyl group in another molecule that's sitting next to it. And so as a result, we have strong intermolecular forces, right? Because we have this strong attraction, which leads to high boiling points and high melting points. It takes a lot of kinetic energy to overcome these forces and to pull two alcohols apart from each other. And as a result, they have high melting and boiling points. So remember, that means too, they're polar molecules and they dissolve well in water typically, because water is a polar molecule too. And you might remember from chemistry 20 that like dissolves like. Polar molecules dissolve well in polar solvents. Non-polar molecules dissolve well in non-polar solvents. Polar molecules do not dissolve very well in non-polar solvents and vice versa. Non-polar molecules do not dissolve very well in polar solvents. So let's try naming a couple of alcohols. Now this is going to be a little bit different because the name, it's not going to come as a prefix, it's going to come as a suffix at the end of the name. So we're going to drop the E at the very end of the parent chain name, and that's going to get replaced with an ol to represent the hydroxyl. So let's look at how it works. Find the longest backbone first, like we always have. So here it goes straight across. I've got a hydroxyl on carbon 2. And I've got a methyl on carbon 3. The hydroxyl is going to take priority over the methyl. I'll upload a document that helps you to see what the priority sequence is. So which things take priority over which other things, in case you're getting problems that are confusing you in that way. But the hydroxyl takes priority here. So, okay, it's got a butane backbone. So we would write it out as butane. And there's a methyl on carbon 3. So it would be 3-methylbutane. To specify the hydroxyl, though, we're going to drop this last E. and we're going to replace it with an OL, but we need a locant to specify where the hydroxyl is. It's on carbon 2. So it'll be 3-methylbutane dash 2 dash ol. Okay, so we've got the an to represent or to tell us that this is an alkane. And the ol tells us that it contains a hydroxyl at carbon number 2. And then this part we've done lots before. There's a methyl at carbon number 3. Let's try a couple here. So we have some alcohols. We have methanol, ethanol, propanol, and butanol. There are actually lots of applications for alcohols, which we won't go into a lot of detail about in this kind of lesson format. But let's start with drawing out some methanol. So methane, so that means we have one carbon in the backbone, right? Because it's a methane backbone. And it has a hydroxyl on the carbon. Now you notice it doesn't have a locant. It doesn't tell you where the hydroxyl is, and that's because it doesn't need to. There's only one carbon, so it has to be on that carbon. So there's my hydroxyl, and then the rest of the things on this carbon would be hydrogens. So there's methanol. Now for ethanol, ethane backbone has got 2 carbons. You notice that it doesn't have a locant. You might say, well, doesn't it need one to tell me if it's on this carbon or if it's on this carbon? But you would start numbering at the hydroxyl, and if it's on this carbon, it would be ethan-1-ol, and if it's on this carbon, it would be ethan-1-ol, and they'd be the same. So that means we don't need to specify which carbon it's actually on. So we can put it on either one, and it will actually be the same molecule. It's just, flipped left to right. And if you were to build it, you would be able to rotate it back and forth and see that it looks the same, that it is the same. So here's my hydroxyl. I put it on one of the carbons, and the rest of these spots I'm going to fill up with hydrogens. Now for propanol, I do need a locant because there are 2 possible places where the hydroxyl can go. It's got a propane backbone, 1, 2, 3 carbons, and this is telling me that the hydroxyl is on carbon 1. So my carbon 1 is one of the terminal ones. I can put it on this one, and then it would be numbered 1, 2, 3. Fill in the rest of these guys with hydrogens. You're probably getting the idea by now. Let's do our last one, butan-1-ol. So it's a butane backbone, 1, 2, 3, 4 carbons. The hydroxyl is on carbon number 1. And maybe we'll make this one a condensed structural. So we're going to fill up the rest of these with hydrogens. Right, and this is then how we've numbered it based on our scheme. So let's try another one where we have to name it. And maybe try pausing the video here and see if you can name it on your own, and then you can press play and see if you got it right. So I'll name it for you. Here's the longest backbone here. Find the parent chain like always. Let's make that a little straighter. Let's find the parent chain like always. We've got 2 methyl groups, and we've got a hydroxyl. Now we're going to start numbering on the right side because that's closest to the hydroxyl. And then I've got a methyl on carbon 2, a methyl on carbon 3. So 2, 3 dimethyl. Did you forget the di? Hopefully not. 2, 3 dimethyl, and then it's butane. I do need the locant because the hydroxyl could have been here. Could have been on carbon 1, but it's on carbon 2. So 2, 3 dimethyl butane 2 ol. Now, if you have a polyalcohol, which you might use your reasoning skills to determine means it has more than one hydroxyl group, poly meaning many, then there's kind of a funny thing that happens with the naming. In our previous names, we've dropped the E, right? It's not butane 2-ol, it's butan 2-ol. But in a polyalcohol, the chemists have decided to leave the E. The E is not dropped if you have a polyalcohol. You'll have to watch this one when you're doing the Moodle quiz if you get a polyalcohol, to make sure that you leave the E in there when you're naming your structure. So here we're asked to draw a structural formula for butane 1,3-diol. So the diol means there's 2 hydroxyls. And you see here, this isn't a typo. That E for butane, it does actually stay there. So let's draw it out. We got a butane backbone, 1, 2, 3, 4 carbons. Let's number these guys. We can go left to right because we get to choose. And then we've got hydroxyls on carbon 1 and on carbon 3. So we can put a hydroxyl here and we can put a hydroxyl here. Doesn't matter if we point them up or if we point them down, or this one could be pointing out this way. Then we're going to fill up the rest of these spots with hydrogens. So hydrogen, 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 and this guy's got 3. Okay, so that's butane 1,3-diol. The last thing that I need to show you before you can try some of these on your own is that cyclic alcohols are named kind of as you'd expect. So this guy has got a cyclohexane backbone, right? Cyclohexane. And just like with a straight chain, instead of being called cyclohexane, it will be called cyclohexanol. Cyclohexanol. Because we've dropped the E, because it's not a polyalcohol. It's just got a single hydroxyl. And then we replace it with an ol. And with other cyclic compounds, if we just have one substituent, we just have one functional group here, we don't need a locant because we always have to start numbering with that on carbon 1. And so it doesn't actually matter where we put it because it's always going to be carbon 1. It's always going to be the same. Now, this guy, hopefully you recognize when you look at it, the parent chain here isn't a cyclohexane or a cyclohexene. That's a benzene. Right? This guy's aromatic. And with the aromatic, you might think, oh, well, I can figure that out. Happy, that's going to be called benzenol. And it's not even a little bit. When you have a benzene ring that's been substituted with a hydroxyl, that gets called phenol. Phenol. So this molecule is called phenol, and that's how it would get named. You don't want to get that mixed up. So do not mix up with phenol. Right? Phenol is what we called benzene when we had to name it as a group. Right? This thing is a phenol. So this molecule would be called 2-phenylpropane, right? So do not mix up phenol, which is benzene as a group, with phenol, which is benzene that's been substituted with a hydroxyl. Okay, so you've got some practice down here. Try the alcohols and halides, and the answer key will be posted.